This is Chemistry of Carbon and its Compounds, Part 4. We're going to be talking about nitration of benzene rings, the Friedel-Crafts acylation, and addition polymerization. The assessment criteria that we'll be looking at is as follows. Understand the mechanism of nitration and the importance of nitration in synthesis. Know some compounds for which nitration is an important precursor. Understand the Friedel-Crafts acylation and its importance in synthesis. Understand that an organic compound with a carbon-carbon double bond will polymerize by an addition mechanism. Be able to draw the repeating units of addition polymers and their associated block diagrams. Appreciate that hydrocarbons used in addition polymerization are largely oil-based chemicals. Understand the mechanisms of some addition polymerizations and know the potential for polymerization of dicarboxylic acids and diols and dicarboxylic acids, acid chlorides, and diamines. Well, let's look here at the nitration of benzene. Now, the nitration of benzene, because of the stability of the benzene ring, requires the making of an electrophile from two strong acids. Nitric acid and sulfuric acid are combined to make a nitronium ion. In the diagram below, see the generation of the electrophile. Once that nitronium ion, a strong electrophile, is made, then it is used to break into the benzene ring. You remember what we saw in the last video about electrophilic substitution on a benzene ring. This is electrophilic substitution, not of a chloride or a halogen on a benzene ring, but a nitrate group. NO2 plus is a strong electrophile, and it reacts with the pi bonds of the benzene to form that intermediate. A hydrogen is lost, and we get nitrobenzene. The following video reviews our understanding of benzene rings and discusses nitration.
Benzene has an empirical formula of CH. It also has an MR of 78. This suggests a structure of C6H6.
I am benzene!
You are unlikely to use benzene in a laboratory, as it is carcinogenic.
Oh man, I don't feel so good.
you're more likely to use methylbenzene, benzene's retarded cousin. In 1865, Kekule suggested that benzene was planar.
Benzene appears to be planar. Flat.
He also suggested that it had an alternating single double bond structure.
Alternating single and double bond structure.
There are now three pieces of evidence that prove Kekule wrong. These include thermodynamic data, if benzene was to have three double bonds, as it says it does, it should have a delta H of 360. It doesn't. Instead, it has a delta H of 208.
208.
As you can see, benzene clearly does not have that structure. Instead, it has been determined that benzene has a delocalized ring of electrons in pi orbitals, which give it for a more stable shape.
Stable.
Other data includes the chlorination of benzene. You do not get anything more than 1,2-dichlorobenzene. Also, benzene cannot be affected by bromine water, as it does not have double bonds.
Not a single one. The nitration of benzene. Easy if you use electrophilic substitution, and don't forget your nitronium ion.
How'd you make it?
A very good question. You take 2 H2SO4 plus HNO3 to get 2 HSO4 minus plus H3O plus NO2 plus.
What conditions?
Concentrated nitric and concentrated sulfuric acid and warm. There we go.
Thanks, mate. Can you show us the mechanism?
Yes.
Fantastic. I look forward to that.
The mechanism.
Babushka.
You take one nitronium ion, one benzene atom, and as the nitronium ion is an electrophile, which is an electron deficient species, the delocalized ring of electrons, some are attracted out of the ring to form a positively charged intermediate. The mechanism, part 2. Here we have a partially unstable intermediate, and to regain its stability, a hydrogen ion is lost, as so, and a normal intermediate is left. But remember, that hydrogen ion is lost. So, at the end of the mechanism, you're left with nitrobenzene. But make sure you keep that temperature under 50 degrees, because otherwise you might get polynitration and TNT.
show some compounds for which nitration is an important precursor. Nitrobenzene is used in many, many formations of compounds that we use in our modern world, whether it to be to make pesticides, explosives, pharmaceuticals, or many other things. We will see nitration of benzene rings. Solvents, soaps, even the analgesic, when you have a headache, when you take paracetamol, you are using a nitrated benzene compound. Understand the Friedel-Crafts acylation and its importance in synthesis. Well, the Friedel-Crafts acylation provides a means of attaching more carbon atoms to benzene rings. We haven't seen carbon atoms attached to benzene rings. So far, all we've seen is nitrates added to benzene rings and halogens added to benzene rings. How do we do this? Well, you see the four-step process. That four-step process uses aluminum trichloride to make the strong electrophile that will work on the benzene ring. It's a four-step process. The basic four-step reaction is benzene plus that acyl chloride gives you a substituted benzene ring with carbon, in this case a methyl group, plus HCl. Let's watch this video that gives us a better understanding of that four-step process. Understand that an organic compound with a carbon double bond will polymerize by an addition mechanism, be able to draw that repeating unit, and know an equation to represent the process. The picture that you see on the bottom of this slide is an ethene molecule, or many ethene molecules that have been broken down at the double bond, and it allows other ethene molecules that have been broken down at the double bond to connect into polyethene. This is called an addition polymer. We saw this last year. Hydrocarbons are used significantly in the making of addition polymers. After World War I, chemical technology was far enough advanced to be able to make plastics in the 1940s and the 1950s. Predominantly, the polymers that were made were addition polymers. In 1954, polypropylene was made, and you have seen that be the basis for packaging, for the making of paper or plastic cups, plastic plates, and even for building insulation. A leader in this was an American company called Dow Chemical. We have on this slide the polymerization of addition polymerization. And I put it on again so that you can see the difference between ethene polymerizing to form polyethylene, plastic shopping bags or plastic bottles, and styrene. Styrene is made into an addition polymer called polystyrene. Notice it's basically the breaking of a double bond, but this double bond is attached to a benzene ring, rather than just another hydrogen. Know the potential for polymerization of dicarboxylic acids and diols. We have an example for you to look at here of ethane 1,2-diol. Notice it has hydroxide ions on either end with an acid, terephthalic acid. And what it does is create a polymer with an ester link. Notice the loss of the hydrogens to create the ester. We have a dicarboxylic acid, no matter the length, mixing with a diamine, and it makes a polyamide polymer. Notice here the same situation going on. What is taken out of the diamine and the carboxylic acid? A water molecule again. Let's have some questions to start your thinking. Again, look and revisit the video about the Friedel-Crafts reaction. In your own words, describe that mechanism. You will have to be able to do this at the end of class 12. Also look at the nitration of benzene and state some reasons why it is so important to the pharmaceutical industry.